Good morning, everyone, to this third day of ADMOS. My name is Håkan Johansson from CIMNE, and I will share this session on optimization and inverse problems. We have 4 talks that we will hear first, and after we have a joint discussion. Please state your questions in the chat, and I will read them during the discussion. First, we have Gabriel Stankovic from Erlangen-Nuremberg, who will talk about embedding domain discretization for coupled topology and shape optimization.
I would like to welcome everyone to my presentation. My name is Gabriel Stankiewicz and I am a PhD student at the University of Erlangen-Nuremberg. In this presentation, I will speak about a coupling of topology and shape optimization, which is possible by employing an embedding domain discretization. I will start with a brief overview of the embedding domain technique. Next, I will introduce the couple optimization method. Finally, I will present the results for the cantilever example. The main feature of the embedding domain method is that the simulated body B is embedded into a larger computational domain omega. The key modification to the bilinear and linear forms is the introduction of a characteristic function He, which indicates whether any point x in the domain belongs to the body or not. Upon discretization of the embedding domain using finite elements, we group them into 3 sets: inner, boundary, and outside elements. In our work, for the treatment of the domain integrals, we oversample the integration points using 5 to 10 integration points along one dimension. Those integration points that lie within the body B fully contribute to the domain integral. If not, their contribution is significantly scaled down. Treatment of the boundary integrals involves further subdivision of the segments at the finite element boundaries. In this way, each subsegment contributes to the nodes of just one finite element. Node-based shape optimization can be performed using embedding domain discretization. The vertices of the boundary segments of the embedded body B serve as design variables. In this way, the shape is explicitly represented by the boundary segments. The computational domain, however, remains unchanged during optimization, and only the segregation of the elements into inner, boundary, and outside sets is updated. Consequently, this approach brings several benefits as compared to the standard node-based shape optimization, such as possible large design changes, design update only of the boundary, simple regularization of the sensitivities, no element distortion. Nevertheless, the main goal of this presentation is showing a possible coupling of topology and shape optimization using the embedding domain discretization. What is our motivation? We aim to create a structural optimization method that offers full topological flexibility, and at the same time the boundary of a structure is presented explicitly. Therefore, our goal was to couple these 2 methods into a single problem. This is possible when the embedding domain discretization method is employed. First, let us observe that both the embedding domain and the design space of a density-based topology optimization problem utilize a perfectly structured mesh. Therefore, we can assign both the shape and the density design variables into the same problem, in which the inner elements of the embedding domain can be assigned a pseudo-density. Finally, we can observe a similarity between the characteristic function He and the pseudo-density. They both specify an amount of material for any point x. Following this observation, we introduce a hybrid function that incorporates the pseudo-density field into the inside of the embedded body B. Furthermore, we adapt the definition of zeta for the numerical implementation in which pseudo-densities are defined for the inner elements only. Within the boundary elements, we have a solid material inside the body and void outside. We purposely did not define pseudo-densities within the boundary elements. The reason for that is to eliminate the dependency of the shape sensitivities on pseudo-density. Now I'll move to the cantilever problem, which was set up for minimization of the compliance with a volume constraint of 50%. The 12 images show the design evolution of the cantilever. The pseudo-densities are represented by the black to white grayscale, and the variable shape is represented by the red line. In iteration 24, the shape generation step is allowed, as the topology of the structure emerged. Consequently, new shapes were introduced in place of the topological holes. From this point, the shape generation function was invoked a few more times as the topology further evolved, and shape merging took place due to shape intersection. In iteration 132, the optimization converged with a smooth design. On these images, a distribution of the shape vertices is shown for two selected final designs. Higher concentration of the vertices at regions with higher curvature was possible thanks to adaptive shape refinement based on two criteria, the curvature criterion and the length criterion. In this presentation, a novel method to couple topology optimization and shape optimization was presented. Such a coupling brings a few advantages as compared to the individual methods, but also comes at a certain cost. What we count as plus is exact boundary representation, full topological flexibility, possibility of large design changes of the shape, same computational domain for topology and shape. We are also aware of the drawbacks of the method, to which we count changing number of design variables and inherently complex optimization problem. That's the end of my presentation. Thank you to everyone for your attention.
So thank you very much. Now we move to the next talk by Hector Juarez of UAM in Mexico, who will talk about numerical solution of the Cauchy problem for the Laplace equation, a deterministic and Bayesian approach.
Hello, everybody. My name is Hector Juarez from Mexico. This time I'm going to talk about the problem of finding a harmonic function defined on this annular region with inner boundary gamma 1 and outer boundary gamma 2. Observe that there are two boundary conditions on the outer boundary and none on the inner one. This problem has several applications, but is ill-posed. So in order to solve it, we define this auxiliary problem here on the right-hand side, in which for each function phi defined on the inner boundary, there is a unique solution of the state equation with a well-defined trace on the outer boundary. This relation defines linear injective and compact operator K, which gives the forward map. So our problem is in operational form is given by relation 2. A way to solve this problem is to find an approximate solution by this penalized problem in which we need to compute the adjoint operator solving the adjoint equation. An equivalent form is used to employ Tikhonov regularization and solve problem 6 or 7. In this case, we solve this problem with conjugate gradient algorithm in combination with finite element discretization of the state and adjoint equations. These are some convergence results, and these are numerical results. In the left figure, we show a 20% perturbation of the exact data on the outer boundary. In the right-hand side, in this figure, we show the solution, the numerical solution on the inner boundary. This is similar results, but with another annular region. The results are very, very good. Now let me consider the Bayesian approach. We first discretize our problem to obtain this problem 9, in which we consider just the relation between the nodal values of those functions, obtaining equation 10. Then if we consider additive noise and Bayes rule, we have to compute this or to propose what is the likelihood function, Py given x, and the prior P of x to obtain the posterior distribution, which is the unknown in this case. We consider additive noise, then the likelihood is defined by this relation 14. And in order to construct the priori model, we use Gaussian Markov random fields. Then the joint density function for x is given by this expression where Q is symmetric positive definite and can be computed by the discretization of the diffusion operator. In our case, we first discretize the first derivative with basic forward discretization. obtaining this matrix D. And then Q is obtained as a multiple of D transpose D, shown here. So putting together the prior and the likelihood, we obtain the full Vagisian model, which is a normal distribution with mean X bar and covariance sigma. One important result here in this work is that different precision matrices Q are related to different regularization strategies for traditional inversion but Tikhonov regularization. It is shown here, that relation between both approaches. So the last step is just to sample the posterior. We use a MCMC algorithm based on the T-walk, known as the T-walk, and we obtain the following results. This is the perturbation of 10% perturbation of data on the outer boundary, and here we show the numerical results on the inner boundary. We have three estimators, and here these are similar results but with a higher perturbation. And this table summarizes the numerical results with different perturbations. These are some numerical, some references. And thank you very much. That's all. Have a very nice day.
Thank you very much, Hector. We now move to the third talk, and I would like to encourage you all to write questions in the chat. The third talk is Chaitanya Dev, a compliant mechanism design with stress constraints using topology and shape optimization, as well as the first talk. This is from Erlangen, Nuremberg University.
Welcome to my presentation on compliant mechanism design with stress constraint using topology and shape optimization. My name is Chaitanya Dev. I am a PhD student at University of Erlangen, Nuremberg. What is compliant mechanism? A compliant mechanism is used to transfer an input force to an output port through the deformation of structural component. To understand compliant mechanism, let us consider an example of force inverter. In force inverter, we are providing an input force in positive x direction on the left wall, and our goal is to obtain a force in negative x direction on the right wall. To obtain this mechanism, we use topology optimization technique. In topology optimization technique, the density distribution of the domain is varied to obtain such a mechanism. On a close examination of the mechanism obtained by topology optimization, we can see hinge formations. These hinges are subjected to very high stresses. To reduce the stresses in these hinges, we use shape optimization. In shape optimization, the design variables are the nodes on the boundary of the structure. We perform the shape optimization using an embedded domain discretization technique. In embedded domain discretization technique, a body B is embedded in a computational domain omega. In numerical implementation, the key modification is introduction of the characteristic function xi to the variational equilibrium equation. Further, the Dirichlet boundary conditions are imposed indirectly with a penalty function. The domain integrals in embedded domain technique is performed by integration point oversampling of the boundary elements. Further, the line integral is performed on the boundary of the embedded domain and the contributions are assigned to the local elements of the computational domain. Coming back to our optimization problem, we introduce a p-norm stress constraint in the shape optimization phase. Again, to evaluate the stresses at the boundary element, we use the characteristic function sheet. The missing component for transition from topology optimization to shape optimization is generation of the geometry after the topology optimization phase. To this end, we use an alpha shape generation algorithm. In summary, the workflow involves topology optimization to obtain the mechanism. Then a geometry is generated using alpha shape generation algorithm. Finally, a stress constraint is introduced in shape optimization to optimize the structure. Here I present the result for the force inverter problem. Here the structure is optimized for 3 different allowable stresses. 300 megapascal is denoted in blue, 200 megapascal in green and 100 megapascal in red. As we can see, for higher allowable stress, we get narrower hinge. In conclusion, we have added stress constraint to the shape optimization phase to minimize the stresses and obtain a design with exact boundary representation. We have the ability to control the thickness of the hinges by prescribing the appropriate allowable stresses. As an outlook, in our numerical experiments, the volume constraints were not satisfied. Further investigation is necessary to strictly enforce the volume constraint. Also, we can impose local stress constraint on the shape elements instead of a global p-norm stress constraint. Thank you for your attention. Have a good day.
Thank you very much. We come now to the last talk on this session. A modular nonlinear stochastic finite element formulation for uncertainty estimation by Yanis Amouche.
Good morning everyone, my name is Yanis Amouche. I'm a PhD student working in the University of Oxford and more precisely in the Department of Engineering Science. I'm working under the supervision of Antoine Jerusalem in an EPSRC project named ADMOS in collaboration with Rolls-Royce. This presentation is about a modular nonlinear stochastic finite element formulation for uncertainty estimation. Traditionally, engineers have been using finite element methods for design purposes. However, these methods fail to capture the interesting variability arising in industrial problems. Indeed, it is impossible to know precisely the material properties of a given component, nor the boundary conditions that are applied. In addition, there might be some defects on the geometry because of the manufacturing process. Thus, the aim of our work is to provide a stochastic finite element solver that will link probabilistic distribution of inputs, such as Young modulus, to the probabilistic distribution of outputs, such as displacements or stresses. To do so, we modify the finite element waveform. In the finite element waveform, a test displacement eta is used to create an equation that allows the derivation of the real displacement and the stresses that are supposed to be space-dependent quantities. In the stochastic finite element waveform, these quantities are now supposed to be space-dependent probabilistic distributions, which means that both the spatial and the stochastic problem are going to be solved in one go. These variables can be expanded as follows, where the function size are either continuous using polynomial chaos expansion, discontinuous using R expansion, or can be both a combination between continuous and discontinuous expansions. It is worth saying that we need to perform basic operations such as multiplication or division during the computation of probabilistic distribution. To do so, it is required to code a stochastic algebra that can be plugged into an already existing finite element solver. This finite element solver can be modified in a modular way in order to solve for stochastic finite element problems. Indeed, the preprocessing part of the solver has to be modified, and also the computation of internal, external forces and the stiffness tensor as well. We now test our method on a bifurcation problem where the output is varying discontinuously with respect to the input. The problem we consider here is a 3D beam that is clamped on its left side and submitted to a stochastic axial displacement on its right side that has a given distribution. There are two regimes. In the regimes where the stochastic axial displacement is tensile, the lateral displacement at the end of the tip is not varying greatly with the displacement. However, when this displacement starts to be compressive, it triggers buckling and thus a large lateral displacement, which is the left part of these curves. It is worth saying that each dot of this curve requires to do one finite element simulation with a given stochastic axial displacement. When we try to use polynomial chaos expansions to capture the dark blue curve, which is the ground truth, we are facing instabilities and more especially a Gibbs phenomena. Indeed, even when increasing the order of this expansion, we only get oscillation around the singularity, which means that there is no convergence. However, when we use our expansions that are intrinsically discontinuous, we manage to capture accurately this singularity. However, the smooth part of the curve is not captured well enough and requires a higher order of the expansion. We managed to get an accurate result using a mixed expansion, which is a combination between discontinuous and a continuous function. And it gives satisfying results with only low probability regions that are not fully well captured. We have to put the emphasis on the fact that only one simulation is needed to get this curve. In conclusion, the method we implemented in a modular way is sampling independent and captures the impact of uncertainty with only one simulation. It is also possible to capture discontinuous distribution using appropriate expansion. It is also more efficient as a factor of 3 of computational time can be spared compared to traditional approaches such as Monte Carlo. This concludes my presentation, and feel free to ask any questions.
Thank you very much, and it's nice to see that there are a few questions, so I take them first from the chat. The first question to Shantanya. Can you elaborate on the sensitivity with respect to the underlying finite element discretization? It's a question from Fredrik Larsson.
Yeah, can you hear me?
Yes.
Yeah, okay. Yeah, thank you, Frederick, for the question. Yes, we use adjoint method to compute the sensitivities. So we form a augmented Lagrange functional with the response function and the underlying BVP, and the test functions of the BVP are considered as adjoint variables, and we solve this adjoint problem to get the sensitivity. Does this answer your question?
No, I think it's more on how does the solution depend on the mesh. If you use a coarse mesh or a fine mesh, will that Fredrik will correct me if I say wrong.
Okay. So to this end, like to accurately represent the boundary, we use refinement on the boundary cells. So in this case, the boundary cells are already refined, but have not run a study where I have used different refinement levels to evaluate the accuracy of the sensitivity. But with whatever
mesh size I was using, I was getting a reasonable sensitivity. So I can't comment on the accuracy because I have not done a quantitative study of how accurately it depends on the mesh size.
Okay.
Yeah.
Thank you.
Okay.
Then thank you. So we move to the other question by Fredrik as well. I hope someone else finds the chat as well. To Janis, in the results, is the buckling always in one direction upwards? If so, how is this controlled in Monte Carlo and stochastic finite element respectively?
Hello everyone, can you hear me?
Yes.
Okay, good morning everyone. So that is a really, really good question, and I would like to share my screen quickly if it's possible to answer to that question. Indeed, before applying the stochastic axial displacement, we apply at the tip of the beam a displacement in a direction, a really, very small displacement compared to the length of the beam, so that the buckling is always going to be in the same direction. The reason why is because if we don't apply this displacement and if we use a symmetric mesh, because the problem is symmetry, the boundary condition of symmetrics, then we do not observe any buckling, just a high, strains, high compression strains, and no buckling. So to observe a buckling, we have to guide it and put an initial displacement so that the beam is a bit tilted before the stochastic axial displacement is applied.
Okay, you can keep it because we have another question.
Okay.
So I take the question from Pedro. Could you comment on the number of queries to the model that are needed to achieve a good probabilistic description of the output?
Could you repeat the question, please?
Yes. Could you comment on the number of queries, I assume evaluations of the model, to the model that are needed to achieve a good probabilistic description of the output?
It depends which methods are we using. If we use Monte Carlo, we should do the simulation a certain number of times. Here we did them 1,000 times. Of course, to discretize this curve, it's not compulsory to do 1,000 simulation. A few hundreds should be doable. For the intrusive methods, only one simulation is required. The main difference is that we must change the number of function psi we are using. The higher the number of function psi we use, the better the approximation should be. So this is why in this curve we used 8 function psi's. So instead of having, I would say, let's say the deterministic problem has 1,000 degrees of freedom, then the whole stochastic problem will have 8 times 1,000 degrees of freedom. Hope it answers the question. If not, feel free to ask me again.
Yeah, it's a question of what you count on the simulation, I suppose. As you said, it will be as number as you have in the expansion of your probabilistic function. How do you choose that is the question from me, actually.
How do I?
How do you know how many you will use? That you have 8 or 4 or?
That's a good question. to know which to know how much we shall use, we use a convergence. We try to increase the number of function and see how quickly it converges. The thing is that it is quite difficult to know before the simulation how many function you will need to approach your problem.
Yeah. Pedro answers that he was concerned about the computational cost, but it's clear that the stochastic method reduces the cost significantly. Thank you very much for your answer. And we have a question to Chaitanya Moore, I think, from Kiran Sagar Kolepara.
Yeah.
The field is, to Chaitanya, the field is new to me. Can you briefly comment on basic differences between the topological and shape optimization?
Okay, yeah. Thank you, Kiran, for the question. Can I share my screen?
Yes.
Yeah. Sorry. Okay. In topology optimization, we are basically varying the densities of each finite element, and based on which we optimize the material distribution, where exactly the material should be to meet our response. And in shape optimization, we are basically moving the nodes of the geometry to achieve a certain performance. So here you can see the nodes are moved to get the desired feature of the structure. And in topology optimization, it's basically varying the densities of the finite element to get the design. I hope this answers your question.
Okay. Okay. Thank you. Get your answer.
Yeah.
Maybe a question to Gabriel then, and maybe that's to both of you in a sense. How this method is, how straightforward is it to extend to 3 dimensions?
So the generation of the shape will be difficult for 3D, definitely. But the shape alpha generation can be also used to generate boundary in the 3D. So that would be triangular mesh. So our goal is also to extend it towards 3D, in which during topology optimization, alpha shape generation will be used to generate 2D boundary that will then be used to further fine-tune the exact boundary position. But that is a difficulty, of course, as compared, let's say, to pure topology optimization. This gives a certain additional complexity. But on the other hand, in pure topology optimization, also a post-processing step is needed to generate certain geometry to interpret the results. So we consider it as a similarity also, that we have to find the actual shape that represents the topological results. And then we would like to use this shape to fine-tune further the design.
Okay, thank you. Related to that, in traditional topology optimization, one has issues with stability. One has this kind of filters and so on. Is this an issue with your method? For Gabriel.
Yes, I'm not sure if I understand your question.
Okay.
Could you
In
say?
traditional topology optimization, like ones in Denmark are very fond of, there is different kind of filters applied or different kind of methods to scale the solution in order to the density field in order to ensure that you have not this checkerboarding phenomena
Yes.
that can arise.
Yes. So basically, to account for that, we use filtering of sensitivities of the topological design. So we use a basic filter radius as also proposed by Ole Sigmund. And basically by applying this filtering to the sensitivities of densities, we get rid of the checkerboard pattern. So that basically fixes the problem. And we also control the complexity of the topology by the choice of the filter radius for the sensitivities.
Okay, so did this method that you use change this in any way or affect this with the shape when you combine with the shape optimization?
Yes, so this is also incorporated in the coupled problem. Yes, so basically there is no checkerboard pattern because of the filtering of the sensitivities. And as soon as the shape is introduced, it drives the, let's say it's dominant in the further stages of the optimization. And at this point, the regularization is important for the shape sensitivities in which the jagged boundaries are omitted. I'm not sure if I understood your question correctly.
No, I was just thinking that if you have a method that avoids these many issues that comes with the traditional topology optimization, leading to checkerboarding. Okay.
Okay, thank you.
Thank you very much for your answers. No more questions in the chat, but I was thinking, listening to Hector's presentation. This problem that you solve, do you use synthetic data for the identification in the example that you show? Or how did you generate that synthetic data, if so?
Yes, the answer is that the data is actually synthetic data. We haven't yet provide data from experiments because the problem I'm solving is a problem that is a subproblem of another one, which is the inverse electroencephalographic problem. This is this problem that I presented arises from that problem, but it is a different one in which there are no data. So we decided to provide synthetic data in order to test the methodology.
Okay, thank you. How did you do this, create this synthetic data using like a finer mesh of the same geometry, or did you do other variation other than adding noise?
No, it was just same mesh. The only thing is that we added different, experiments with different data, adding different noise. So that's the way we provided different error in the data. And our interest was to test how this error propagate when we apply the methodology that we propose. So we are very concerned about control the error. finding the unknown. And the results show that the methodology is a good one in that sense.
But you consider the geometry as known, to my understanding.
The geometry of nodes?
Yes, or the computational domain.
Oh yeah, the computational domain is, as I said, is fixed. The only thing that you have to take care of is what are the nodes on the outer boundary and the nodes on the inner boundary. So there is a relation between those nodes. You can also provide designed. For instance, saying how many nodes do you need in the outer boundary, which is where we have the data, in order to capture the solution in the inner boundary. So there is a dimensional analysis that I didn't present in this talk because it takes more time to explain and more experiments. But yes, and there is a relation between the exterior and interior nodes. For instance, if you have more data than unknowns, you actually don't need regularization in order to find the solution. But if it is the opposite, then you certainly need a stabilization technique in order to get results. I don't know if this answers your question.
Yeah, to some extent, because I'm thinking about the engineering application of the issue, where you have the same problem, but you might be a little bit unsure on the exactness of the geometry from some CT scanning or similar.
Yeah. Okay.
And how
in
this
this case,
uncertainty would affect the solution.
we are assuming that we have the exact geometry, because in experiments you are interested on the in a school or the head, etc. You can scan. From scans you can reconstruct the geometry, and once you have the geometry, then you can pose the problem and solve it in some way. So we are not the issue here is not like in shape optimization, in which you don't know what is the shape of the inner boundary in this case, which is that you don't know. I mean, here is very important to have the geometry in with the to have to know the geometry in a acceptable way in order to solve the problem.
And I think it would be very good to know what is acceptable way, what kind of resolution is needed so that it doesn't affect the solution that you want to the solution that you want to identify.
Yeah, of course. I mean,
would be a fun
acceptable in the sense that, for instance, you have a patient, you are in a medical, diagnosis of, I don't know, epileptic focus, and you solve the real problem, then you need to reconstruct from scanners the geometry. So the geometry is attached to every person. So in that sense, is that I say that you need an acceptable geometry or representation of the real geometry.
Thank you very much for your answer.
Thank you.
Are there more? No, I don't see any further questions in the chat. No. Since we have a few minutes left, I think maybe I should ask Yannis again, because I'm also new to this stochastic finite element. You mentioned different basis functions, phi, epsi, that could be polynomial chaos expansion or HAR or mixed. I wasn't a bit fully sure what these mixed basis functions look like, and not the others either, I must admit.
Can you hear me?
Hello?
Yeah.
We have a little bit problem hearing you, Janis. It's a bit background noise or something.
Is it better now? Is it better?
Very tough. We can hear something at least.
Okay, and now can you hear me?
No, much better.
Okay,
Yes.
cool. Okay, I'm going to share my screen and to show you the basis function. It's going to be easier that way.
Yes.
Okay, so I'm just going to show you some article where these functions are. This function. Okay, so this is how the mixed expansion look like, and instead of f, just replace this function by psi, and normally you should have a good intuition of what these functions are. So you see the scale is between -1 and 1. So basically what you do is that it is possible to map the probabilistic distribution of output from -infinity to +infinity to 0, 1, where 0, 1 is where the float, the double between 0 and 1, is the cumulative distribution of your probabilistic distribution. So, and then you do, then it is possible to map the domain 0, 1 to the domain -1, 1. And this is the mixed, the value of the, what the functions of the mixed expansion look like. How a different order, they might be different, but you can, the main features that you can see is that they are discontinuous, and they are smooth as well. So they allow you to capture both singularities and smoothness at the same time, which is not possible with the two other expansion that either capture smoothness or only capture discontinuities. So I don't think I have the R function on the paper, but basically R in German I think it just means hair. So it's just some staircase functions. And the polynomial.
I think that was a good answer. What I was looking for.
Thank you. And yeah, to finish with the polynomial chaos or purely polynomial function with no discontinuities.
Thank you very much.
Welcome.
So I think it's, I would like to thank all the speakers for good presentations and good discussion afterwards. So I am to tell you about the next session that starts at 10 o'clock. So now we have 12 minutes to get a cup of coffee or tea or what you prefer. And I thank you very much, all of you, for the attention for this session and looking forward for the coming sessions. So thank you very much.